Welcome back. The last few lectures we have seen how nonlinear models are quite different from linear models. We also reached some kind of definition of a solution to ordinary differential equations. In the case of linear systems, we actually found a solution to the generic linear differential equation. Whereas when it comes to nonlinear systems, basically, essentially, we have this equation, x dot is equal to f of x of t, and we have no idea how to go about solving this in general, right? I mean, we had some specific examples where we did this trick of rearranging in differential forms, and then we integrate it and so on. In the linear case, we had this technique of multiplying with the exponential and things like that. But however, in general, we didn't really develop any technique in terms of how to solve this, and it's not easy, right? So, what is the problem that we are trying to solve? We have this differential equation. Let's identify slowly each of these things. So this x dot is a function, of course, which came from taking a derivative of x of t. So essentially, the main thing that we are trying to solve for is x of t, which is a function, right? And of course, we have no clue whether it has to be at exactly equal to 0 or some interval around it or whatnot, right? All those questions will come up. But essentially, we are trying to find a function x of t that fits exactly this particular equation. So when you take the derivative of x of t, it will give another function of time. When you apply this f on this x of t, you will again end up with another function of time, and both right hand side and left hand side have to be same, right? So how do we ever reach a point where we know how to solve this particular problem? Well, one way of thinking about it is somehow magically somebody gives you an answer. At least we have a way of checking that, right? We can substitute in both sides. One, if you have x of t is equal to some function, let's say t square, x dot is 2 times t, and then you take t square and substitute in f of whatever the function. So f of t square hopefully is equal to 2t, and that will tell us at least it solves, right? Then the questions will come up. We know that basically there could be possibility of multiple solutions. Is the solution valid for entire time? All those questions are still unanswered, but at least if we have one solution, we can verify if it is indeed a solution. But when we don't know even that one single solution, then we have no clue. So it's not an easy problem in general, right? There are special classes of systems like linear differential equations. We know how to solve them. The standard technique that these days we employ is, of course, put everything in MATLAB, some numerical tool. And essentially what MATLAB does is the following. It approximates this x dot as some kind of, in this particular case, I'm just taking brute force first order approximation, right? So which is nothing but difference between x of t plus delta t minus x of t is divided by delta t is equal to f of x of t, right? By rearranging, we essentially get something like this. So x of t plus delta t is x of t plus delta t times f evaluated at x of t, right? And this is so-called Euler approximation. One can use, you have things called Euler approximation of derivatives. Okay, and there are other methods where we approximate derivatives with higher order. There are techniques called Runge-Kutta techniques, and we can use those and then try to solve this particular problem. And we will end up with basically bunch of numbers essentially starting from x of 0, where we have an initial condition, x of delta t, x of 2 delta t, and so on and so forth, right? And then of course here delta t smaller the better, So if we have a really small delta t, we get better approximation. That's something that we know from numerical analysis, right? But will we ever get the exact solution? Can we actually verify that this is indeed a solution? Unfortunately not. We just basically, through this technique, we basically get a bunch of numbers at various values of time, but discrete sequence of times, and then we can never therefore understand what's going on between x0 and x delta of t, and we need to do something like interpolation, extrapolation, and when we do that, there are different ways of interpolating extrapolation, and then basically once we do that, then perhaps we can at least check if this particular differential equation is satisfied approximately for that particular interpolation, but never like exactly satisfying this particular equation. And of course, one may question for applications, should we really worry about exactness, or is approximate good enough? But that's where the more fundamental question comes into picture. Do we really know that this particular equation has a solution, in which case this is a valid method? Meaning, what I'm saying is any numerical method that we want to use in practice makes sense if we know somehow theoretically there is an answer to the question that we are trying to solve. In this particular case, we are trying to solve an ODE. If the ODE to start with does not have any solution, then this technique seems to be providing that solution no matter what. So there is a mismatch between the theoretical prediction of having no solution versus numerical technique always providing a solution, and that may seem very subtle and unnecessary difference, but in reality it matters quite a bit in terms of actually validity of a particular model. If it doesn't have a solution, if it doesn't have a solution, that perhaps is a wrong model because it may not represent ever the actual physical model. So those questions will come up. So blindly one cannot use a numerical technique without knowing anything about existence of solution of this original equation. And as I just pointed out, this is a very complicated question. How do I know, how can I find this particular function that satisfies this equation exactly, unless we have some special class of problems where we have seen how to do linear models, for example, and a couple of other simple equations by doing a differential form and things like that. So, hopefully you appreciate the complexity of this particular problem, with us. And so this lecture, essentially, we will, do something slightly different. We will take this differential equation, write it as something called integral equation. The name is fairly self-explanatory. And then, of course, we'll try to understand through this integral equation how to address the problem of existence of solutions. It's still not easy, right? Essentially, that's what we are going to do. So before we do that, much of the material for this particular course is inspired by a book co-authored by Haddad and Chalaboina, 2008 edition of Nonlinear Dynamical Systems and Control. It's a Princeton University Press publication. And of course, if you want some additional material on these topics, and either ordinary differential equations or stability theory that will come in later weeks, I suggest these two excellent books, one by Professor Vidyasagar, Nonlinear Systems Analysis. The latest edition is published by SIAM in 2002. And another old book, again republished recently by Springer in 2002. It's a book by Bhatia and Ziago on stability theory of dynamical systems. Both are quite self-sufficient, really well-written books. But much of the material for this particular course is taken from the first reference. So again, not to repeat myself many times, but it's good to recall a few things about things that we have done so far. LTI models, the linear models, are quite straightforward and we have seen how to solve them. Whereas nonlinear systems, as we just repeated again the argument, they are quite complex. Solutions may or may not exist. Solutions may always not be unique, and the solutions may exist only locally, right? So all these complexities will force us to understand them theoretically, because otherwise numerical solutions could have been appropriate. And that's what we're going to try to do next. So what we'll do now is basically look at this differential equation and rewrite this one as an integral equation, but let's put some notation here. So x dot equals f of x of t with initial condition x of t 0 is equal to x 0. For what values of t is this going to be valid this equation, differential equation? Well, we will have some notation I x 0, which is essentially going to depend on where you start with, and it's called maximum interval of existence. That means if this particular equation has a solution starting at x 0, remember the solution is not just satisfying the differential equation form of it, but actually also the initial condition. So if some equation is some function x of t is satisfying this differential equation starting at x 0, then the understanding is perhaps there is an interval of time for which this particular equation is valid, right? So we don't know whether that interval could be empty also. That means there is no solution at all, but it could be very small or big, infinite time interval it could be, right? So anyway, that's just for notation's sake, and then we remind ourselves that we are calling any function x of t as a solution if it satisfies the ODE and the initial condition, but it's also continuously differentiable, right? And at least for the sake of this particular course, we will assume that continuous differentiability, right? And it doesn't take much work to realize that this differential equation can be written in the form of an integral equation. It's just a matter of integrating that equation. Of course, one has to convince ourselves that this is indeed equivalent. I mean, certainly x dot equals f implies this integral equation. But if we do have an equation that satisfies this, showing that it is an ODE, so showing that it satisfies the ODE takes a little bit more work, and I leave that as a thinking exercise for you. So essentially, now the question of solving the differential equation boils down to solving this integral equation. So before addressing the actual question, I want to introduce one more notation, and this is a very important concept that comes up several times. So I'm going to spend a few minutes in terms of discussing this notation. This is a very much more general concept than specific solution to ODE or something like that. So we call that concept as dynamical system. Dynamical system has three animals in it, triple. First one is basically a subset of Rn. It could be Rn itself, n-dimensional real space. And the second one is the real space. The first one is talking about where this, loosely speaking, this dynamical system lies, and then the first one, right, the D corresponds to the space where this dynamical system lives in, and then R is the second R corresponds to the time aspect of this particular dynamical system. The word dynamical simply means changes with time, right? So there's something changing in time in that space D, right? What is changing? It is essentially represented as a function that is mapping from R cross D to D. So that means something that starts changing as time changes, but always lives in this world of D, right? And then we are not going to just say this S function is arbitrary, but we actually associate certain things true about this particular function. So this S as a function of two variables is continuous, and as a function of the first variable, it is continuously differentiable for every x, which is the second variable, and it satisfies this so-called initial condition equation, where S of 0 comma x0 is x0 for all x in this space D, and we have this interesting condition that basically, if we essentially it boils down to, if I'm going to start at, let's say, x0, I move to a particular time, and I move another tau seconds or tau units of time from there, then the solution starting from x0 till t plus tau time units is same as if basically it's tau minutes after I started from this S of t comma x0. It's a fairly straightforward condition that we put if we say that somehow this is related to the solution of ordinary differential equation, but in reality we are defining a very abstract concept of dynamical system, and then this dynamical system is entirely defined by the space and time, and then finally the function that lives in this space, right? So as I just indicated, basically if x of t is a solution to differential equation for that particular initial condition, we capture both the initial condition information and the fact that it is a solution to some kind of differential equation. We captured that by this function s of t comma x0. Now I just want to ensure that you understand why we introduced this notation beyond using this for doing some interesting mathematics. But so for example, in some cases this function may not be continuous, right? So that means it may not be a solution to some differential equation, but in reality there are systems which could be discontinuous in real world, and then we want to model those. So this is a nice way of capturing such systems. They may actually be satisfying not differential equations but more general forms of them, hybrid models, specifically impulsive differential equations, and so on and so forth, right? So in that sense, looking at this very general concept, it could be quite useful, and at a later point we use this notation to see certain behavior of these dynamical systems. But as far as this course is concerned, this s of t comma x0 comes from solution of a differential equation. Though as you'll see, some of the things that we conclude may not ever directly depend on f, and in general conditions on s may be derived without knowing much about f, right? So we can rewrite the ODE as an integral form, we have already seen, and then but in the notation of this s of t comma x0, which we will call that as a flow. So in the notation of flow, we can write the ODE as s of t comma x0 is equal to x0 plus something, right? This integral. So essentially, what is the question of existence? Does there exist a flow s of t comma x0 such that it satisfies that equation that is in front of you, right? So it's like looking at basically an answer point in this very weird space that satisfies both sides of the equation, right? Except that point actually happens to be a function of two variables. So essentially it boils down to looking at this particular integral equation, but it's not so easy. As I was saying, basically this may be viewed as some kind of equation of the form y equals p of y, where this p kind of represents the integral on the right hand side, and y represents this very complicated function called flow s of t comma x0. But at a very high level, it's like looking at this equation y equals p of y, and such equations are solutions to such equations. We call them as fixed points. So essentially, this particular problem boils down to something called fixed point problem. One standard technique, not the only technique, one standard technique to solve fixed point problems is write this y equals p of y as yn plus 1 is equal to p of yn, since we know what is p, and then maybe start off at some initial condition y0 or something, and then apply this iteratively and hope that it converges. One can actually show, depending on the conditions on p, if such an algorithm converges, it converges to a fixed point. The questions in terms of there are multiple answers to that, and those things are still very difficult to address, but at least there is a way to show that if you have a sequence that is coming from this recursive equation converges, then we have a solution, right? But it's much simpler than said than done. So if we know that there is an answer to it, then perhaps we can start searching for it. If we don't, then where do we start, and does it always converge? All these things are again questions. In fact, this problem belongs to again the question on a dynamical system of a different nature. These are discrete time equations that we have barely spoken about in first couple of classes or so. So this is indeed a question of dynamical systems again, but it's of a simpler kind, if you will. But the summary again, I'm going to repeat it myself many times, is there is a way of thinking about this problem, but not so easy, right? It doesn't guarantee any answer. So we have to seriously look into some of the theoretical aspects of fixed point theorems, right? So I'm not going to get into some of these details, and one has to look at the literature that I have shared to see how to solve this particular problem, right? So before I show you a very specific example, I want to motivate that what we're going to see here, right? So let's pick the problem of solving. I mean, this is not quite ordinary differential equation, but this is more along the lines of this recursive equation that I was talking about, just to see the complexity of a very simple problem also that we are trying to solve through recursive equations. So we all understand that solving finding square root of a positive number is essentially solving the equation x square is equal to a. Right? Hopefully a is positive in this particular case. Of course, we can write this as x square is equal to a as x equals a by x, right? And so that's like writing that ODE as y equals p of y, right? Same thing in that same sense, x equals a by x. So then basically put this n and n plus 1 and then make it recursive. Xn plus 1 therefore becomes a by xn, right? And hope that for certain initial condition it can be solved, right? The other way of thinking about it is x square is equal to a may also be written as x square plus x is equal to a plus x. Okay, I mean, why not? You can create infinite more flavors of this x square is equal to a by adding, subtracting, all kinds of things, and then basically you will get equal number of recursive equations. For every such modification, you'll have a recursive equation, and the recursive equation in this particular case is x of n plus 1 is equal to a plus xn divided by xn plus 1, and then hope that for some initial condition this will provide us an answer, right? So does it? Well, let us actually see if we can do that experiment. I have written a code in MATLAB, and let's hope that this works. Hopefully you're familiar with how this works. So if you look at the code, I started with a equals 2, x equals 0.9, some number, it doesn't matter. And then I use the first recursive equation, x equals a by x. That's the recursive equation I used the first time around. And when I do that, I didn't write this code in such a way that it shows the entire set of steps. There are 1,000 steps I've chose. You can sit down and think about it yourself. Basically, 2 by 0.9 is essentially something like what is it? It's approximately 2.22 or something like that. And then when you actually take 2, when you go through the second recursion, you'll get 0.9, and then you'll keep shifting between 0.9 and 2.22 for as many number of times you run this particular program. So if you choose the number of steps as 1001, you would have seen the answer. Perhaps we can try that. So I'm going to, for some reason this is not working. Yeah, okay. So let's not disturb it. Basically, it's seems that it keeps on recursing between jumping between 0.9 and 2.22, right? And certainly that's not a good algorithm. I mean, we have kind of concluded that if the sequence, the recursive equation sequence, converges to something, then that converged point actually is a solution to the fixed point problem. So that gives us an answer. So I'll do the same initial condition x equals 0.9, but then I use the second recursive equation, right, which is essentially recursing xn plus 1 is equal to a plus xn divided by xn plus 1. When I do that, and for 1,000 steps, I get x equals 1.4142. And if you see actually the sequence, you will see that this is indeed converging, and that converging point happens to be 1.4142. and we know that it's approximately square root of 2. And I've tried many numbers other than 2, and then every time the first algorithm gives some kind of jumping behavior, transient behavior that never converges, whereas the second algorithm seems to be always converging, right? The question becomes, why one converges and one doesn't, and then that's beyond the syllabus of this particular course at this time, but it does fall into the category of actually understanding not differential equations, but difference equations, and in that sense, understanding difference equations is as complicated at times as what we are seeing in this particular course. So anyway, so this point of this example is to understand that just because we can rewrite in terms of a fixed point problem doesn't mean that we have a way of solving the problem, right? So what do we do next? We have seen that finding roots of an algebraic equation may be solved using a recursive algorithm. The result depends on the convergence of the algorithm, even in a simple square root of type of problem. And the integral form of ODE is far more complicated than a simple algebraic equation like x square equals 2, and hence it's almost impossible to use it as an algorithm to solve ODEs. So essentially, this is nice to know that we can write ODE in an integral form, but it doesn't provide an obvious algorithm to solve, right? So that's essentially the difficulty of ordinary differential equations. But fortunately, mathematicians looked at such fixed point problems in a very, very abstract sense, and actually they have proven multiple theorems in terms of how one can guess if there is a solution and things like that. And the pioneers of ordinary differential equation theories have actually used these theorems and provided as answers to the question of existence and eventually uniqueness of these solutions, right? So this introductory lecture on ODE solutions is essentially saying we can write ODEs as integral equations. That's a nice way of putting it as in the form of a fixed point problem. Unfortunately, we don't get an algorithm out of it, but we do get a nice way of attempting to solve that particular problem through these very abstract fixed point theorems applied to your integral equation, right? So the next lecture is going to be actually looking into specific theorems of existence and uniqueness. Thank you.